Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh, everyone. This is part 3 of optimization problems. It is essentially referred to applied maximum or minimum problems. Okay, before we start, let's try to recall the 5 steps to solve any optimization problems. The first step is, of course, you need to understand the problem and then find an equation to maximize or minimize. Then, step 2, you need to reduce this equation to just one unknown variable. And then step 3, you need to take the derivative of the new equation that you just found in step 2 and then set it equal to 0, alright, to find the critical values. Now, step 4 is to verify the critical values that you get and determine whether they are maximum or minimum. And the last one is you have to answer the question being asked. Example 3. This example is taken from your DM025 notes. Okay. A window has the shape of a rectangle surmounted by a semicircle. The diameter of the semicircle is equal to the width of the rectangle. If the perimeter of the window is 12 cm, find the dimension of the window so that the greatest amount of light is emitted. Now, I have this window. Okay, this is a rectangle. Alright, on top of this rectangle is a semicircle. And this semicircle has a diameter here. This is the diameter. Okay, so this one is the diameter. Okay, from the center here to the side, this is the radius. So the diameter is double the radius, that is 2r. Okay, now the diameter of the semicircle is equal to the width of the rectangle. Okay, now the diameter is 2r, so the length of the bottom here of the window will be 2r. Okay, now two of the sides of this rectangle, okay, are the height of the window and they are equal, so we can call that h. So that is the height. Okay, now this question says the dimensions of the window, find the dimensions of the window so that the greatest amount of light is emitted. Now this phrase, greatest amount of light is emitted, okay, this phrase means we want to maximize the area of this window. Okay, so now our optimization equation would be the area equation of the window here, but with a constraint. What is the constraint? The constraint is the perimeter of the window must be 12 centimeter. Well, 12 centimeter I think is actually very small for a perimeter of a window. Maybe this is a window of a Mickey Mouse house. Okay, but never mind. Before we move further, we need the tools or the formula that we will need to solve this problem. That is the area of the rectangle and the area of the semicircle. Okay. Now, the area of the rectangle is equal to the length multiplied by the width. Okay. The area of the circle is equal to pi r squared. Okay, now our goal is to maximize the area of the window. So now step 1 is to find the optimization equation, that is the area equation. Now the area of the window here, alright, is equal to the area of the rectangle, okay, plus the area of the semicircle. Okay, now the area of the rectangle is the length multiplied by the width. What is the length? The length is 2r. So this is 2r, and the width here is the height, that is h. Okay, plus the area of the semicircle. The area of a circle is pi r squared. So the area of the semicircle is 1/2 multiplied by pi r squared. Okay, now this is the optimization equation. Okay, now this optimization equation is in two variables, r and h. Okay, we need to reduce this equation to just one variable. It is either in terms of r or in terms of h. Okay, now the question says the perimeter of the window must be 12 centimeter. So let's come up with the secondary equation, that is the perimeter equation. Now the perimeter equation, alright, the perimeter equation is equal to the just the left, the bottom and the right part of the rectangle plus the outside part of the semicircle. Okay, the outside part of the semicircle. The outside part of the rectangle is h plus 2r plus h. Okay, now the outer or the outside part of the semicircle is 1/2, okay, multiplied by the circumference of the circle. So we know that the circumference or the perimeter circumference of a circle is equal to 2 pi r. That is the circumference of a circle. So this is a semicircle. So that is 1/2 multiplied by the circumference of a circle, that is 2 pi r. Now you can simplify that, and that would be 2r plus 2h plus pi r. And this perimeter is equal to 12 here. So that is 12 centimeter. Okay. Now you can go ahead and simplify this. Maybe you can take 2h as the subject here. So that would be 12 minus 2r minus pi r. Okay. This one you can plug in the area equation. We can go ahead to step number 2. Step number 2 is to reduce the area equation or this optimization equation into just one variable. So our area equation is A, that is equal to R. We rearrange the equation, multiply by 2h, alright, plus 1/2 multiplied by pi r squared. Now we are going to plug in this 2h in here, alright, because we want to reduce this a into just one variable. So 2h is equal to 12 minus 2r minus pi r, okay, and then plus 1/2 multiplied by pi r squared. Simplify that, and that would be 12r minus 2r squared minus pi r squared plus 1/2 pi r squared. Okay, you have pi r squared here, you have pi r squared here. So you can simplify these two terms, and that would be 12r minus 2r squared minus 1/2 pi r squared. Okay, now your area equation or your optimization equation is in one variable only. Now we are ready to take the first derivative to get the critical value. We go to step number 3, that is to take the first derivative of A. Now the third step is to take the first derivative of A, so that is A prime. A prime is equal to 12 minus 4r minus 1/2 multiplied by, okay, bring the power that is 2 here down, okay, in front, multiply by pi r, and then the power here you have to subtract by 1, that is 1. Now simplify that, it would be 12 minus 4r minus pi r. Okay, this is your first derivative. you need to set this first derivative to 0 to get the critical value. Okay, so now 12, you can factor the r out. So r multiplied by 4, this one should be plus pi. Alright, now r multiplied by 4 plus pi, that is equal to 12. So your r is equal to 12 divided by 4 plus pi. Okay, now this is your radius and this is the critical value. Please note that this pi here, alright, this pi here is not a variable. This is a constant, okay? So you can calculate this one using your calculator. This r is approximately 1.68 centimeter. Okay, to confirm whether this radius, okay, actually maximizes the area of the window, we need to use the second derivative test. Okay, now we go to the step number 4, that is to take the second derivative of a. A prime, our a prime is 12 minus 4r minus pi r, that is a prime. First derivative, this is the second derivative. Second derivative is equal to minus 4 minus pi. Okay, pi is a constant, so this is actually a negative number. Minus 4 minus pi is actually a negative number, that is less than 0. Well, this is a good news. Why? Because if the second derivative is negative, our critical value here is going to generate a maximum value. Okay, now you can conclude that R equals 1.68 generates maximum value. Okay, now we go to step number 5, that is our last step, to find the dimensions of the window. Okay, now the radius is equal to r, that is equal to 1.68. The width of the width, width, alright. The width of the window is 2r, that is 2 multiplied by 1.68, and that is equal to 3.36. Okay, centimeter. This is all centimeter. And last one is the height. Okay, the height. Okay, we know from here 2h is equal to 12 minus 2r minus pi r. 2h is equal to what? 2h is equal to 12 minus 2r minus pi r. 12 minus 2r minus pi r. So that is equal to 12 minus 2r is 1.68 minus pi multiplied by 1.68. Then we want to get the height of the window. This value is divided by 2. Then you will get this one is about 1.68 centimeter. Okay, now the dimensions of the window, we have the radius here 1.68 centimeter. The width is 3.36 centimeters and the height is 1.6 centimeter. Okay, so that's the end of part 3.